Guys, spanning tree, that is a network protocol that ensures a loop-free topology for Ethernet networks. It prevents broadcast storms and network instability caused by the redundant paths. So again, the purpose of spanning tree is loop prevention, and STP detects and disables redundant paths to prevent loops in the network, which can cause broadcast storms and the network congestion. So how it works, STP designates a root bridge based on the lowest bridge ID, which I will show you how it will be calculated. Then STP calculates the shortest path to the root bridge and places other paths in a blocking state to prevent loops. So the key thing here that we need to know is Ethernet frames don't have a TTL value such as an IP packet. So they can move between switches eternally, guys. So for example, let's say this PC1 is creating some broadcast traffic and this traffic is reaching to the switch 1. You can see in here we have two different colored arrows, okay? The one with the green arrow and the other one is the red arrow, okay? So what will happen, this switch 1 will forward this broadcast traffic from all of out its ports. It will just flood it, right? From this direction, shown with the green arrow, and from this direction, shown with this red arrow, right? Then this switch 2 will have this same broadcast packet and it will continue flooding it with the direction of this green arrow. The same will reach to switch 3 and switch 3 will also continue to flood it out. Okay, so there is a flood and there is a broadcast storm in two directions. The first direction is on the green arrow direction. The second one will be on the red arrow direction. Okay, so moving forward, why we need spanning tree? The second answer is to prevent unicast duplicate frames. Okay, so for example, let's say this switch 1 is trying to send some packets to PC2. Okay, this packet will reach to switch 1 and switch 1 has no idea where this PC2 is connected to, right? And it will just send this packet from this port as well as from this port, right? So the traffic will reach here, switch 3 from this port, and it will reach to switch 3 again from this port. So what will happen now? We have a unicast duplicate frames issue, okay? So to prevent both scenarios, unicast duplicate frame issues as well as the broadcast storms, we have this spanning tree protocol. So spanning tree, it builds a logical loop-free topology for Ethernet networks, and how it achieves it, it is just going ahead and blocking some of the available ports. Okay, so it basically allows a network design to include redundant links to provide automatic backup paths if an active link fails. So what will happen by the help of the spanning tree protocol? Let's say it will go ahead and block some of the ports for switch 1. Let's say according to algorithm it is blocking this port. So what will happen if PC1 generates some traffic? This traffic won't be flooded out from this interface this time, and there will be only one direction. This frame can be forwarded out and frame will reach to PC2, and there will be no communication over this port of switch 3 since the other side of the switch 1 is in blocking state. So you can just ignore this path as of now, and you can think the topology will really look like in this way. Okay, this one, switch 1 connected to switch 2, it is connected to switch 3. So you can think here there is a redundant path. Of course, the cabling will remain same, but it will only take into place if there is a problem with these cables or with one of these devices. Okay, it will remain in blocking stage until there is a problem with this traffic flow. The root bridge, that is the primary switch in a spanning tree topology. So it serves as the reference point for all other switches in the network. And how I am electing the root bridge is the root bridge is elected based on the bridge ID value, which consists of the priority, which is a configurable value, and the MAC address of the switch. Always the switch with the lowest bridge ID will become the root bridge, and in case there is a tie, the switch with the lowest MAC address will win it. Okay, so all path calculations and port roles are determined based on the root bridge's position in the network, and it serves as the focal point for calculating the shortest path to all other switches in the network. Okay, so the root bridge forwards traffic to and from other switches, ensuring the efficient communication within the network, and all designated ports on other switches send traffic toward the root bridge while root ports connect to it. Okay. So, in spanning tree protocol, each switch port can assume one of several roles based on its function in the network topology. So, some of the key port roles are, the first one is the root port. Root port on a non-root bridge that has the lowest cost path to the root bridge. Okay, so this port is responsible for forwarding traffic to the root bridge. On the other hand, the port on a network segment that has the lowest cost to the root bridge and is responsible for forwarding traffic to and from that segment is the designated port. Only one designated port is active per segment, that is very important, ensuring that traffic is forwarded efficiently without loops. And the last state is the blocked port, a port that is not currently forwarding frames because it has been placed in a blocking state to prevent loops, is known as the blocked port. So it prevents network loops by disabling redundant paths while still listening for BPD use to maintain awareness of the network topology. In summary, root port is the port with the lowest cost path to the root bridge on non-root bridges. Okay, designated port is the forwarding port for traffic on a segment, and blocked port is the blocked port. So let's have a look to the topology that you are seeing on the screen. I have my root bridge in here, that is switch 2. Okay, so I have my fast Ethernet 00 and fast Ethernet 05, fast Ethernet 04 and fast Ethernet 01 ports of the switch 1 and this switch 3. So fast Ethernet 01 and fast Ethernet 05 are the root ports because they are closest to the root bridge in terms of cost. Okay, so costs are assumed same in this example. Let's assume this path has a cost of 1, this path has a cost of 1, this path has a cost of 1. So Fast Ethernet 00 will be the root port for switch 1 and Fast Ethernet 05 will be the root port for switch 3. Okay. On the other hand, designated ports are Fast 02, Fast 03 and Fast 04. Okay, those are the designated ports. And I have one non-designated port that is the blocked port, which is Fast Ethernet 01 for this example. I will go through, other examples as well. Just bear with me. You need to have a good understanding when we end up this session. Spanning tree path cost is a value used by spanning tree protocol to determine the best path from a switch to the root bridge. Okay, so each interface on a switch has an associated cost based on its speed. So for example, a link with 10 megabit per second has a cost of 100. A link with 100 Mbps has a cost of 19. 1 gigabit Ethernet link will have a cost of 4 and 10 gigabit per second will have a cost of 2. So lower cost always indicate faster connections. Okay, just keep in mind. Let's continue with this example again. Cost of path 1, that is calculated as 19 because that is a fast Ethernet link which is a 100 Mbps. Okay. On the other hand, the cost for path 2, it will include this path as well as this path. It is 19 plus 19 equals to 38. So when I'm trying to reach the root bridge, I have my path from switch 1, of course. I have my path 1 and path 2 options, and path 1 has a cost of 19, path 2 has a cost of 38. So lower cost 19 indicates a faster connection. So path 1 is preferred over path 2. So here I have one question. Okay, spanning tree port roles question. The question is asking me which switch is the root switch. Then you need to determine the port roles. Okay, just have a look to topology, or maybe you can try to pause the video and try to answer those questions before I jump into the answer. And let's now jump into the answer. Okay. So here is the answer. Which one is my root bridge? That is the first question. So root bridge is the bridge which has the lowest bridge ID. And the bridge ID includes the priority value as well as the MAC address. First thing you need to check is the priority value. If any other switch has the lower priority compared to others, that will take over the root bridge role. Okay. If this one is equal, if priority is equal, then you need to check the MAC address value. Whichever has the lowest MAC address, it will take over the role for the root bridge. Just have a look into the screen. You will see all of the switches has the same priority value. Okay. Then what you need to do, you need to check the MAC addresses. If you check the MAC addresses, you will be able to see every MAC address of the switch starts with 0011 and 80. Okay. After 80, there are some different numbers. For switch 1, it is 7. For switch 2, it is E. For switch 4, it is C. But for switch 3, it is 3, right? So it is 3 for switch 3. So that means switch 3 has the lowest MAC address, and that means also it will become the root bridge for this environment. So our root is switch 3. When it comes to the roles, port roles, first of all, you need to know one thing, okay? So each switch, guys, other than the root switch, must have one root port, okay? One root port should be for each and every switch except the root bridge itself. So how I am finding the root port? That is the fastest path, lowest cost path to reach to the root bridge. Okay, so for this case, for example, switch 1 Fast Ethernet 01 will be selected as root port because it is directly connected to the root bridge, right? On the other hand, I have to find which is the root port for switch 2 as well as for switch 4. For switch 4, it is very easy because I have this interface which is connecting to my switch 3, my root bridge directly, right? So GIG02 will become the root port for my switch 4. For switch 2, I have two different options. It could be this port or this port, right? If I have a look to this port, from here to there is a gigabit Ethernet connection. I know that gigabit Ethernet connections has lower cost compared with the fast Ethernet connections, right? And if I go from this direction, there is a link which includes gigabit and fast Ethernet, okay? And there is another link which includes fast Ethernet and fast Ethernet, okay? Since this one and this one equal, fast giga, so the cost is same for this. However, for these paths, the lower cost will be for this path because this is connecting a giga link, okay? It will have a lower cost compared with this path. So the lowest cost that I can reach my root bridge from switch 2 is via GIG01 interface. So that is why I am assigning my GIG01 of switch 2 as the root port. So remember what I have told you. Each segment should have at least one designated port. Since I picked root port as GIG01 in here, the switch 4 GIG01 will be my designated port for this segment. Since I have my root port GIG02 of switch port in here, switch 3 fast02 will be my designated port, and since I have my root port in here, switch 3 fast01 will be my designated port. But what about here? There is one switch which is switch 1, and there is another switch which is switch 2, and none of them are the root port, right? But I know I should pick one designated port for each and every segment, and the other port should be the blocking port anymore, because there should be at least one blocking port in the spanning tree topology, right? How I do the election, why this gigabit 02 is not the designated port, but it is the blocked port for this topology. Okay, let me tell you the answer. Now, if you face with something like this, you compare this time switch 1 priority with switch 2 priority, which is equal. Then you compare the MAC address, and whichever has the lowest MAC, it will grab the designated port role. For this case, it is switch 1, okay? And what will happen? Switch 2 GIG02 will be non-designated and blocked port for this example. Okay, great. I hope it is clear enough. If you have any questions, just feel free to raise from the Q&A section. So let's continue with the types of the spanning tree protocol. So there are 5 types of the spanning tree protocol. They are STP, PVST+, Rapid STP, Rapid PVST+, and the MSTP. So when it comes to the properties of these different spanning tree protocols, you could see that the resource needed, which means running the STP protocol will consume some of the CPU and the memory of the switches. Okay, the resource needed for STP is the lowest, where the Rapid PVST+ is the highest. Okay, when it comes to the convergence, STP and PVST+ is the slowest ones, and the other ones is very much fast. How I am doing the tree calculation is per VLAN for PVST and Rapid PVST+, all VLANs for STP and RSTP, and per instance for MSTP. So PVST+. PVST+, that is an enhancement of spanning tree protocol, and that creates a separate spanning tree instance for each VLAN in a network. So that is to allow a better load balancing and optimized traffic management. So different VLANs can have different route bridges and active paths in this PVST+. Okay, so PVST+, it is compatible with both standard and rapid STP, making it versatile for mixed environments. So as you can see in the screen, what PVST+ is doing, it is creating a separate spanning tree instance for each VLAN. Okay, so for example, for VLAN 1, this one is the route bridge. For VLAN 2, however, this switch is the route bridge. Okay, so for example, this port of this switch, that is a forwarding port for VLAN 1, however, it is a blocking port for VLAN 2. Okay, so when it comes to Rapid PVST+, that is an enhancement of PVST+, that implements the rapid spanning tree protocol features. Okay, so as name implies, Rapid PVST+ provides fast convergence. Okay, so it provides significantly faster convergence compared to standard STP and PVST+, allowing the network quickly adapt to topology changes. So like PVST+, again, it maintains a separate spanning tree for each VLAN, allowing for load balancing and optimal traffic flow. And the port roles, when it comes to the port roles, this protocol, Rapid PVST+, introduces additional port roles like alternate and backup ports to enhance redundancy and failover capabilities. What are the benefits of using Rapid PVST+? It is for quick recovery from link failures or topology changes, minimizes network disruption, and it also provides faster convergence, leads to better performance and more efficient use of network resources. So in spanning tree protocol, each port on a switch can be in one of 5 states. Okay, so these states determine how the port handles the traffic and its role in maintaining a loop-free network. So blocking states, as you know, the port does not forward frames and only listens for BPDU. Listening state is the state where the port prepares to forward frames, okay, but it does not send or receive any data. In the learning state, the port begins to learn MAC addresses from incoming frames but does not forward any frames yet. In forwarding state, the port actively forwards frames and learns MAC addresses. And disabled state is the state which means the port is administratively shut down and does not participate in spanning tree protocol. Okay, so when it comes to the RSTP, Rapid Spanning Tree Protocol, that simplifies the port states to enhance the convergence speed and efficiency while maintaining a loop-free topology. Okay, in Rapid Spanning Tree Protocol, ports can be in one of the three states. Okay, so these states facilitate faster convergence and enhanced network efficiency compared to the traditional spanning tree protocol. So as you could see in here, there are discarding states, which is equivalent of the disabled, blocking and the listening states of the STP. So in the discarding state, the port does not forward frames and does not learn any MAC address in RSTP, and that is very similar to the blocking state in STP. It prevents loops by not participating in data transmission. On the other hand, we have learning as well as the forwarding port states, which is the same as like in STP. Okay, so however, when it comes to the port roles, STP has root designated and blocked port roles. On the other hand, RSTP has root designated and it introduces alternate backup and disabled port roles as well. In Rapid PVST Plus, we have something called edge ports. Okay, they are a specific type of port that plays a crucial role in rapid convergence of the network. Okay, so an edge port is a port that connects directly to the endpoint devices such as computers, such as printers, rather than to other switches. So edge ports immediately transition to the forwarding state without going through the listening and learning states. This allows for quicker access to network resources and endpoint devices. Okay, so if we have a look in here, I have my Fast Ethernet 07, which is an edge port. I have Fast Ethernet 08, which is an edge port because they are directly connected to the endpoint devices such as PCs, right? So that provides fast convergence. And how I am configuring this edge port is by using this spanning tree port fast command. Okay, so edge ports don't generate topology changes when the link toggles. So if you just make a test, if you are able to make a test with a physical switch, when you connect this PC to this switch port that you configured with PortFast, you will be able to see the link will become up like a charm. So whenever you plug this cable, the link will become up and go into the forwarding state like a charm. However, for the ports that you are connecting one switch to another, you will not be able to see port is going into the forwarding state that much fast. Okay, so Rapid PVST Plus link types help define how ports on a switch interact with the network and their roles in maintaining the spanning tree topology. Okay, there are three primary link types. The first type is the edge link, which connects directly to an endpoint device. The other one is point-to-point link, that is a link connecting two switches directly. And we have link type shared, that is a link connects multiple devices to a switch, such as with hubs or with repeaters. So when you have a look to this screen, this is a link type edge, directly connected to the PC. This is a link type point-to-point, which connects one switch to another directly. This time, this is also the same P2 point-to-point, but this one is shared because this switch is connected to another device that is a hub device, okay, and this hub is connecting to this PC. So that means this is a link type shared.